Welcome back, my warrior Pandus. This is your Captain Shreyas. Good evening, and welcome to the NCERT line by line series for all the NEET aspirants as well as the board aspirants. In depth from the basics, chapter by chapter, paragraph by paragraph, section by section, line by line, decoding by your very own Captain Shreyas Sir. And today's chapter, first part of Moving Charges and Magnetism. Right? So let's begin with the class, and this is your captain, your favorite physics master teacher, guys. And let's begin with the class. And I hope you guys are doing awesome. And maybe you have just forgotten to do one simple task. Yes, what is the task? Every time I have to remind you, quickly smash that like button and subscribe if you are new to the channel, or else you will not find these classes. NCERT line by line, nobody is doing in English. Nobody cares. For all the students in South India, Northeast, abroad, and so many cities where people want to learn in English and in a proper decoded manner, in a beautifully explained manner. Alright, so let's begin. Hi Suganya, hi Krishna, Satyashri, welcome Jasmine. Hello. Good evening. I hope you guys are doing fabulous. Welcome aboard. Already the chat box is fired up. Hi Pratibha, hi Disha. Nice to see all of you. And you guys have been eagerly waiting. Same here. Let's begin with the class. Awesome. Chalo. Let's start. Now, see, in this chapter, basically, with the first time we are starting off with magnetism after electrostatics. And everybody must have played with magnets at some point or the other in your life. So, this concept of magnetism, or these miraculous materials attracting each other, was actually known a long time back, right? Almost 2000 years, right? And it was only 200 years ago, which is just in probably 1820, that it was realized that electricity and magnetism are actually related, and there are many scientists who were actually involved in this. See, we know gravitational force, we know nuclear force, we know electric force, we know magnetic force. So these are like our fundamental forces in nature. People then realize that actually electric force and magnetic force are the different avatars of the same thing. Like maybe I dress up like a Santa Claus, I will behave like a Santa Claus. Maybe I dress up like a proper, school going kid, and probably I act in a movie. Probably you will be like, sir, you're acting so well, sir, as a school kid. I dress up like a teacher. I'll be like, yeah, fine, I'm a teacher now. So same way, electromagnetism, they are basically the same thing. They just dress up differently, they act differently, and sometimes you find them to, show electric forces, and then you see them showing magnetic forces. So they are just manifestations in different forms. Okay, so electromagnetism are interlinked with each other. And the person who demonstrated that was none other than Oersted. Oersted was that guy who related first time experimentally that actually that electricity and magnetism are basically they are related to each other. They are basically related to each other. It's like sometime you meet somebody somewhere. Oh, you're from that city. Oh, I am also from that city. Oh, you know that person? Yes. How are you related? He's my uncle. Oh, you know what? He is my grandfather's brother, something like that. Oh, we two are related. So like that, they found out that they are related to each other. They are interlinked, and it was demonstrated by Oersted. And what did he do? We'll come to that in a bit. If there is an experiment which is mentioned here, and he's all those observations which he noted are mentioned over here. The first thing which he says that the magnetic needle gets deflected when there is a current passing, and the deflection is more when you are close to the wire, and it is less when you are far away, and the deflection increases when you increase the current, and it reverses on basically reversing the current. So basically Oersted was the guy who concluded that moving charges or currents produce a magnetic field surrounding the space. Okay. So, let me tell you what exactly he did. So, this is your, oops, what just happened? Oops. Okay, yeah. So, Oersted, what he did was, imagine you take a wire which carries some current. This is a wire which basically carries some current. He took a magnetic needle. He knew that there are some materials which basically, deflect when you place it near another magnet, or because of the Earth's magnetic field, they start, aligning themselves like your magnetic compass. He saw that this particular magnetic needle, it got deflected, basically deflected when it was placed near a current carrying wire. Now, what is current? Flow of charges, meaning motion of charges. So that's why he thought, when charges move in a wire, when motion of charges occur, then there must be some magnetic effect which is happening, because of which this magnetic needle got deflected. Otherwise, if there was no current, this needle did not deflect. So hence, he concluded that, moving charges or current produce a magnetic field in the surrounding space. Then what he sees is that so these are the conclusions. If current is zero, then the deflection is basically zero. If current is present, then deflection is also present. Also, next thing he sees, if current is increased, then he sees that the deflection also increases. Then he also sees, if distance is increased, then he saw the deflection reduced. And finally, if current is reversed, then even the deflection is reversed. If it was deflecting this way, then it will deflect the other way. These were the observations which are mentioned in this particular paragraph. These were basically the observations. All these are basically the observations which is explained in the next slide. Right over here. All these are the observations. It is written down in a very boring paragraph manner, but if you look at it like this, then it makes sense. So, from this, what is the feeling that you get? The feeling that you get is, if you are close enough to the wire, there is stronger magnetic field. If you are far away from the wire, there is lesser magnetic field. Field is something where you can feel the aura, you can feel the effect, you can sense that there is something. Like some teachers, when they enter the class, they generate a positive field, motivating field, a learning field around them. The closer you are, you might want to sit on the front bench because the teacher is very interesting. But when the aura is very negative, you might be like, okay, I can sit at the back bench. So same way, guys, the closer you are, the stronger the aura or the presence which is felt by the magnetic substances. So the distance reduces, the aura increases, the current increases, the field increases. There is no current, then there is no deflection. If the current is reversed, then the magnetic field reverses the direction, and that's why the deflection also reverses. All right, Hayatluru Krishna, very good. Nice to see you back. Is this point absolutely clear till this point? Everybody with me on this? What Oersted saw? So from this, he was able to talk about something called as magnetic field and all of that. We'll come to that in a bit. Then they are mentioning about all the scientists. This is okay. In this chapter, we'll see how magnetic field exerts forces on charged particles, etc. We'll also learn how currents produce magnetic field. We shall see. It's talking about what we will see in this chapter. That's okay. On magnetic, we adopt the following convention: a current in the field emerging out, and okay, all these are fine. And basically, this diagram is very, very important. I'll tell you, explain you this diagram in this terms. See, if you look at the top view, if you look at it from the top view, meaning like from here, if you see, you will see the current coming towards you. That means I will show the current like this. A current coming towards you will be shown like a dot. This is out of the plane of the particular figure. Similarly, if somebody sees from below, that person will see the current going away. So it will be shown like a cross. It is in the plane of the figure. In the plane of the figure. This is your standard convention which you have learnt even in vectors. A vector coming towards you is a dot. A vector going away from you on the paper is shown as a cross. It's like an arrow which is coming towards you or going away from you. So say for example, you are seeing like this, and it so happens that the current happens to come towards you. Then it is found that the deflection comes in such a way, or if you sprinkle some iron fillings are very magnetic in nature, they can get magnetized. Those iron fillings align themselves in a very peculiar manner, and that looks something like this. These iron fillings, they orient themselves like this. So you can see they are aligned themselves in circular manner, and you will see that their concentration is more when you are close. As you go far away, you will see there will be very few iron fillings which will tend to align as circular loops. So it is basically saying that there is a very strong magnetic field over here, and here the magnetic field is basically weak. So this is how they orient. If you reverse the current, if they were aligned like this, now they will be starting to align exactly opposite. I mean, they will look the same. It's just that they will flip. The north pole will become the south pole. The south pole of the iron fillings will then become the north pole. These iron fillings will flip the directions, and you will still see that they are circular. So it confirms with the observations whatever he saw, and he was able to then relate that electricity is related to magnetism. Magnetism is related to electricity. So the interlinking happened by experimental demonstration. I hope this is clear. And that is exactly what has been mentioned over here, that dot cross. Here they just tell what we are going to study, what we are going to study, what we are going to study. Okay, fine. There is nothing that we can underline over here. Main thing here, how do the magnetic field lines look like, iron fillings look like, that is something which I have already shown over here. Alright. Now, see, I will explain you in a very simple manner. When you have a stationary charge, then what happens? The stationary charge might create your electric field. It will create your electric field, and this electric field, when it passes through another charge, then that charge experiences a force. That force is given by charge which you have kept over here, into the electric field which is generated by this particular charge. This particular thing we have seen even before in the previous chapter of electrostatics. I hope you remember. Force is charge multiplied by field. But if you have current carrying wire, then it is basically now creating a magnetic field around it. It is basically creating magnetic field around it. obviously a magnetic field can affect any of these two things. What are those two things? First, it can affect other magnets. It can basically affect. When I say affect, that means it can apply a force. It can apply a force on other magnets. Example, let's say you have a bar magnet with north and south pole, or for example, a horseshoe magnet with some north pole and south pole, and so many more. So it can apply forces on other magnets. You place a bar magnet, it will be deflecting. You place a horseshoe magnet, it might attract, repel, it might apply a torque, something will happen. This is one thing on which it can apply a force. The other thing which it can affect is basically moving charges, or basically currents. Current is also charges under motion, so moving charges or current. So in this particular chapter, mainly we focus our attention on this. In the next chapter, you basically study this, but mainly in this chapter we study the affection how the magnetic field affects the motion of charges or currents. Is this absolutely clear, my dear warriors? Everyone, let me know. Yes, Krishna, QE. Yes, Madhumati. Thank you so much, Atluru. Please suggest me some tests weekly, chapter-wise for improvements in the comment section. Definitely, Suchi Mama. I read your comment that you have taken some admission and you'll be following the classes here, and time to time guidance you'll be seeking. Definitely, Suchi Mama. Why not? You have been my long-term student. I'll definitely be mentoring you. You can definitely leave a comment. Okay? Yes. All right. So, this is what we'll be studying. This is later on. That is what they have in fact told also. We shall see how magnetic field exerts forces on moving charged particles or current carrying wires. See this? This is exactly what they have told. In this chapter, we'll be studying how magnetic field exerts forces on moving charged particles or current producing magnetic fields. Okay? This is what we are going to study. Anyways, now in the starting part, they remind you of the previous chapters, like how electric field is produced. We have seen this. Electric field is kq by r square due to a point charge, and the force is field into the charge. All these things are reminders or revision of the previous chapters. We have seen this. Due to a point charge, if you measure what is the electric field, it will be kq divided by basically r square. And that same field will apply a force which is given by charge into field, which is exactly what I have told you over here. And this electric field due to a point charge is kq divided by r square. But if you write it vector wise, it will be r hat. This is just a unit vector, nothing great about it. Just to represent the direction. That's all. That is exactly what they have also written over here. No point writing the same thing. Now this was for electric field, but the problem is for magnetic field. How the magnetic field will apply a force. The force by electric field is given by QE. Okay, the force by electric field is given by QE and the field value is given by this. How will magnetic field apply a force is what we are interested in. So, there were a lot of experiments which were performed. So, this is exactly like a introduction or warm up, you can say, before they actually come to the formula or the final theory. They found out experimentally that it obeys all the fundamental laws like superposition, and the direction of the magnetic field is magnetic force is slightly weird. It's not as simple as the force of electric field. And they found out experimentally, before going ahead, I'll show to you over here. If you take a charge and move it with some velocity like this, and let's say there is magnetic field around it. Now magnetic field, you might be wondering, sir, what is the unit, what is the symbol, etc. So see, my dear students, magnetic field, okay, has the symbol of basically B. This is basically your symbol, of course. Okay, this is basically your symbol. It is a vector quantity. It is a vector quantity, and the unit is basically Tesla. The short form is T. There is also another unit which is called as Gauss, and a Gauss is 10 to the power -4 Tesla. This magnetic field follows all those other properties which electric field obeyed. For example, you will see that if a magnetic field line is like this, then if somebody happens to draw a tangent to this at any given point, if somebody draws a tangent to it, then the direction in which the field is going along the tangent, that gives you exactly the direction of the magnetic field. They use the symbol B, not E, please mind it. Also, you will find that if you take two magnetic field lines, this cannot happen. They can't intersect, just like electric fields. They can't definitely intersect. This is not at all allowed. Similarly, if the magnetic field lines go like this, here the magnetic field is definitely very, very strong because they are crowded. Whereas if you go over here, they are very, very far away, so the field is basically weak. So the strength is decided by how closely they are packed or how far they are. And by chance the magnetic field lines are just parallel lines, then such a thing is just called as uniform field, as uniform magnetic field. There is one small difference though. Tamil movies, I will definitely continue this series, but I'm seeing that the motivation is going down day by day for many students. They are losing track. If you lose track and if you don't attend the series, then I will be like, okay, you guys don't want it. You guys again want some chapter 1 only. Again, fine, I'll start with some chapter 1. But if you continue watching, and how will that happen? See, you might be sincere, but you have to motivate your people around you. See, what happens in many channels, especially these Hindi channels, these students form groups. They tell, listen, this teacher is teaching. He's teaching for us for free. And you know, every student is attending the classes. But the same thing when we do for our students, especially our South Indian students from Northeast and even students abroad, you too have to have that same feeling because nobody else is doing. And we can also say nobody is doing, okay, chill, we will also not do. But no, we want to be a revolution. We want to make sure our students succeed. We want to make sure our students get ranks at national level. As simple as that. So guys, please make sure that every student around you is motivated and watching all these classes. Every student around you should be subscribed to the channel and watching all the lectures. It's for free. What am I asking? Just watch the lectures, download the PDFs properly, be sincere, give the tests, whatever we are doing, just do it on YouTube also. You might be a part of some coaching, that's okay. But continue. Alright? There is one thing which is different. Which is not there in electric field, and that is you will never see a magnetic field start and end somewhere. You will always see the magnetic field line wherever it started, it will end at the same point, meaning there is no start or no end. You can take anything as a starting or the ending point. So magnetic field lines, you will see they are always in the form of closed loops. That is very different. So they don't, what do they don't? They don't start, basically, they don't originate or terminate. They don't originate or basically terminate. That is a very different thing fundamentally as compared to electrostatics. Okay? Because you cannot truly figure out the north pole or the south pole of a magnet. You might be wondering, sir, how? I mean, I thought the magnetic field lines start from a north pole and they end on a south pole. Yeah, that is what you thought until school or probably before this lecture. If this is north pole, this is south pole, I'm pretty sure you thought that, okay sir, magnetic field lines originate here and they terminate here, just like a electrical dipole. But actually it is not so. They continue even inside like this. These lines continue even inside like this. If you compare it with electrostatic charges, a positive charge and a negative charge, the different story over here is, here also the field lines go like this. They start from positive, go on to negative like this. But remember, they don't continue like this. Rather, from the positive only, they go like this towards the negative. So you can see inside this dipole, it's still going from positive to negative, but inside the bar magnet, it goes from negative to positive, that is south pole to north pole. South pole is considered as the negative magnetic charge. North pole is considered as the positive charge of magnetism. Not in coulombs, but in magnetism. Getting my point? So you can see they are same but different. Same but different. Right? Is that right, everyone? Same but slightly different. So very important, they do not start or originate anywhere. It's always in the form of closed loop. Unit is Tesla, it's a vector quantity, and they don't intersect. It can be strong when they are close, and if they are parallel, it's basically a uniform field. So coming back, if a charge is in motion, and then I tell you, listen, that there is a magnetic field over here acting like this, it's a vector quantity, then the force acting on it happens to be something like this, but you have to visualize this in 3 dimension, my dear students. It's not only perpendicular to the magnetic field, but it is also perpendicular to the velocity. Very interesting. It's perpendicular to the velocity. It's also perpendicular to the magnetic field. This is the magnetic force acting on it. Very interesting. Usually in our head it is like wherever is the field, that's where the force is and all that, but that was in electrostatics. Force is in the direction of the field, but here the force is in perpendicular direction of the field. Field is here, force is perpendicular to that. You have to visualize this in 3 dimensions, my dear warriors. This is something like in 3 dimensions, which you will have to visualize. Imagine a plane, that gray plane contains B and V. Perpendicular to that is the force. If velocity is here, magnetic field is here, force is perpendicular to this particular plane. It's like this. And the value of this force, the value of this particular force comes out to be charge into velocity cross producted with the magnetic field. Cross producted with the magnetic field. So it involves a cross product. That is something which you need to be very careful about. So this is the magnetic force, magnetic field, magnetic field's force on a moving charge, on a moving charge. Is that clear? That is the magnetic field's force on a charge which is moving. You will see some special conditions over here. One of the first special condition will be, say for example, if it is at rest, if the charge is basically at rest, that means what will happen? The velocity will be 0. You will immediately see that the force acting will also be 0, because 0 into any number will be 0. Makes sense. 0 into any number is basically 0. Not just that, just imagine this, the second special case. Say for example, velocity is parallel to the magnetic field, or it is basically velocity is anti-parallel to the magnetic field. This is also another case. In such conditions, what will happen? Theta will be 0 degree or theta will be 180 degree. V cross B will be VB sine theta. That theta will be 0 parallel, anti-parallel is 180. So in either of the two cases, the sine angle will be 0. Sine 0 is 0, sine 180 is also 0. So that also means that the force will be 0. So if by chance you see the charged particle going like this or like this, this is your charged particle going either parallel to the field or anti-parallel to the field, nothing will happen to the charge. It will continue its journey. There will be no force acting on it. This is what this formula also tells, and experiments also that were conducted followed these same things. Is this clear, my dear warriors, till this point? Everyone fine till this point? Another interesting thing which happens over here is this. Since force is perpendicular to the velocity, velocity is in the direction of displacement. If it is displacing here, velocity is here, force is perpendicular to that. Force, when it is perpendicular to the displacement, what will be the work done by it? What will be the work done by such a force? Put it up in the chat box. Force into displacement, but with cos theta is the work. Cos 90, guys, is 0. So the work done, therefore, the work done by it is nothing but 0. Yes, it will not do any work. And if it doesn't do any work, what does it mean? It can't change its kinetic energy. Remember work kinetic energy theorem? Work changes the kinetic energy. W is equal to delta Ke. If no work, no change in its kinetic energy, which means the speed can't change. The speed can't change. So such a force acting on a particle, don't think this vector of velocity will become long or small. It can never change it, but that force can change the direction of it. So very, very important, but it can change the direction of the motion. It can change the direction of the motion. Very, very important thing. It can't change the speed, but what can it change? Very, very important. It can change the direction. Very crucial, important conceptual points that you are learning over here. Very good. Excellent. That is also what is explained over here, but there is something more to it which will be coming in a bit. Now, imagine there is a charge and it is, let's say, moving like this. So, there is a magnetic field which is acting, and apart from that, there is one more field, and that is, let's say, your electric field which is acting. So many fields are there. Electric field is also there, magnetic field is also there. Let's think one by one what will happen. Because of this magnetic field, if you do V cross B, if you basically do velocity cross B, V was here, cross B will give me the force. So V cross B gives me the force of magnetism. So the force of magnetism due to the magnetic field will be like this. Now of course it will be perpendicular to this also and this also. At the same time, do not forget this electric field will also apply a force on this charge, and maybe that force happens to be like this, and that force will be the electric field force. Both the forces are acting together. Together, when they act, they will superimpose and they will produce the net force. So if I use parallelogram law or triangle law or whatever vector addition law, I will be able to create the net force acting on it. This is using superposition. So by superpositioning the net force acting on it will be F. The net force acting on it will be F, and it will be the force of magnetic field plus the force of electric field. How much is the force of magnetic field? We just saw it. It is charge into velocity cross producted with the magnetic field, and at the same time, what is the force by the electric field? It is plus QE. Q is the charge, E is nothing but the electric field. That is your total force. This type of combination of forces by superpositioning to find net force of magnetic and electric, this is also called as the Lorentz force. This is also called as the Lorentz force. Very, very important, guys. And this is exactly what has been written down over here. If you notice, this is exactly that same statement. Is that clear? And they have told that we can also superimpose and all of that, if you notice over here. So they have mentioned this. They have mentioned this right over here. It is found to obey the principles of superpositioning. The magnetic field of several sources in the vector addition of the magnetic field of each, blah, 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 blah. Okay. And then they tell over here, if there is a point charge moving with some velocity located at some distance in the presence of magnetic field, the force which it will experience is this. This was given by Lorentz, hence it is called as the Lorentz force. Okay. And like you said, see over here, it obviously depends on the charge, velocity, magnetic field, as well as the electric field. Okay. So these are the basic things which it depends on. Now they have also given you the conditions when the force is 0. I have already given you these conditions in this particular part, right over here. If the force is 0, either the charge is 0 or the vectors are parallel or anti-parallel. That's the same thing which they have given in these pointers over here, if you notice. Okay, so you can see that if they are basically, if the velocity and the magnetic field are parallel or anti-parallel, then the force becomes 0. Okay, I hope this is clear. The magnetic force is also 0. The magnetic force is also 0 if it is charge is not moving. That means the velocity is 0. All these points they have mentioned exactly the same way. All right. I hope this is clear. All right. And they have also specified the unit of Tesla right over here. Okay, SI unit is Tesla. The Gauss unit is 10 to the power minus 4 Tesla. And the Earth's magnetic field, just remember this value, is very, very small. Just look at this. Just look at this. It's in the range of 10 to the power minus 5 Tesla. 10 to the power negative 5 Tesla. That's how small Earth's magnetic field is. That's how small Earth's magnetic field is. If you are wondering how Tesla was defined, it was actually defined by this formula. I know the unit of charge, it is Coulomb. I know the unit of velocity, that is meter per second. So, force is in Newton, so magnetic field can be easily defined. How? Just go back over here, where did the field thing go? Yeah. So, since force is equal to QVB, can I not say, therefore magnetic field is force divided by QV, therefore I can just write 1 Tesla of field is when 1 Newton of force, 1 Newton force acts on a Coulomb of charge when it is moving a meter, per second. When it is moving a meter per second perpendicular direction, because then sin 90 will be 1. So that is the meaning of 1 Tesla. Force is Newton, Q is Coulomb, velocity is meter per second. So that's how they define it, and that's exactly what they have done over here. Newton, second, Coulomb, meter, and all of that. This unit is basically called Tesla. The units of be Newton second coulomb meter. Okay. I hope till this point everybody is clear. Understood? Give me a thumbs up. What is the meaning of Lorentz force and everything? All right. Now, before going ahead, let's do one thing. Let's just solve some questions so that you guys get a heads up or understanding of how to use this. I will give you some examples and you are just going to tell me which direction is the force acting on the moving charged particle. That's all you have to tell me. Okay? Chalo. Let's see if you guys can do this. This is the charge. E is electric field, B is magnetic field. E is electric field, B is nothing but magnetic field. Okay, that's all. So many diagrams are shown, some places electric and magnetic both are acting. So there might be a net force also, who knows? Okay, let's do case by case. Start off with this, then go to this, okay? So many examples are there. Let's do this. Come on, Atluru, Jasmine, Disha, Sukanya, Madhumati, Krishna. Come on, everyone. Let's go. Evening Star, Tanuja, come on. Let's go, guys. Let's start solving these questions. Maybe in your rough book or in your rough sheet, you can start doing it. So first of all, if you go over here, the first problem, only electric field is there. So only electric force will come. Only electric force will come. So the force obviously will be in this direction. Same direction as the field. That's it. That's how the force will be. In this case, only magnetic field is there. So the force will be in the direction of velocity crossed with magnetic field. Use your right hand thumb rule. First point the fingers in the velocity direction. Slowly turn it towards magnetic field. The thumb is coming towards you. So the force is like a dot. Force is like a dot. Remember, you have to use cross product. You have to use basically cross product, like I said over here. V cross B is the force. Use your right hand thumb rule. Okay. Next. Here, no matter what the velocity is, force of electric field always will act in the direction of electric field. So the force is in this direction. This was electric force, this was magnetic force, this is electric force again. Okay, next. Here, velocity is here, magnetic field is towards you. Use your right hand, point it in the direction of the velocity, slowly move it towards you. The thumb goes up. Hence, the force acting due to magnetic field will be in the upward direction. Just check this out. It will be upward direction. Here, what happens? The charge is not moving. So, actually speaking, the magnetic component of the force will be 0. Because no velocity, no force. Only electric field's force will be there, just like here. The force of electric field will be in this direction. Is that right? Very good. Next, let's go over here. Oh, this is magnetic field. Velocity is up 180 degrees. So the magnetic field's force will be 0. Parallel or anti-parallel, magnetic fields never apply magnetic force. Let's go over here. Same story repeats. Same story repeats. Magnetic field will not apply any force. But what about electric field? That will just apply the force in the direction of the field. That's it. Fe is in the direction of the field. Here, magnetic field is parallel to the velocity. So the magnetic component of the force is 0. Electric field will definitely apply a force over here. That's it. That's how it works. Let's take another example over here. It is given to you that it is an electron and that electron is going downwards, and it is told to you, listen, the magnetic field is right over here. Can you figure out where is the direction of the magnetic force? Quickly think and tell me. Where is the direction of the magnetic force? Velocity is down. You will have to really twist your hand, guys. Velocity, hold your right hand like this and move it slightly in the direction of B. V cross B, it is coming towards you. So be careful. V cross B is towards you. But there is a problem. I'm multiplying with a negative charge. This is negative charge, so it will change the direction. So hence, it will make it exactly opposite. That's why the force will be in the plane. Lot of people will tell out of the plane, but that is a wrong answer. Got it? It's a negative charge, so be careful. If it was a proton, then it will be towards you. Cool? Let's do one more question coming up on your screen, guys. Imagine again there is a negative charge, negative E or negative Q charge, let's say, and it is going like this, and the magnetic field is inwards. Magnetic field is inwards, and let's say the electric field is downwards. Electric field is downwards. Come on, think about the forces due to each one of them. Think about the forces due to each one of them in this particular question. First, velocity is towards your right hand side. Magnetic field is inside. So place your right hand 4 fingers towards the right. Slowly bend it inside. The thumb will point in the upward direction. So therefore, the magnetic force is in this direction. But the electric field will apply a force in this direction. Now whichever is more will dominate, and the net force will be in that direction. In this case, the forces are opposite, may or may not be equal. That depends. Okay, but they are definitely opposite to each other. That is what we are seeing. So I hope now you understand how to find out the net force acting on a moving charged particle, whether it is positive or negative. In fact, if you notice, one of these statements also mentions the same thing. The force on a negative charge is opposite to that on a positive charge. Very important line. The force on a negative charge is exactly opposite to that on a positive charge. So that is the reason why in these problems, we first find V cross B. V cross B would be out, but the moment you multiply it with a negative charge, it will go inside. Same thing over here also. V cross B was here, but it is a negative charge. So whatever the force was expected, you will have to draw it in the exactly opposite direction. So V cross B will be up, but since it's a negative charge, the force will be downwards. Same way, electric field's force QE should be downwards, but because it's a negative charge, that force of the electric field should be technically upwards. So because of this minus sign, this is the final answer. Otherwise, for positive charge, it would have been up for magnetism and it would have been down for electric force. Got it? Yes, Krishna. So the direction will change. So that was the point which I wanted to make over here. Okay, so that's why I made you underline this. Now, I wanted you to see this. So all these things are important, small things. Cool. Now, I think they have done the examples later on. So we can do this example and then we'll come back. Okay. We'll do this particular example and then we'll come back. If the magnetic field is parallel to the positive y-axis, okay, x is right, z is up, y is inside. So basically the magnetic field is inside the plane of the board. You can see that crosses. Cross means going away inside the plane. And a charged particle is moving along the positive x-axis, which way the Lorentz force for an electron and a proton be acting. Okay, the magnetic field is there. So guys, very simple. Magnetic field is inside. The velocity of the charged particle is right over here. So if you do V cross B vector will be right over here. First put in the V direction, then B, it will be upwards. So if it was a positive charge, versus a negative charge, then on the positive charge, the Lorentz force would be like this, but on a negative charge, the force would be exactly opposite. That's the only difference. Got it? Positive charge, it would be like this. Negative charge, it would be like this. Something very similar to this example. Because it was negative, we had to reverse the direction. Is that clear, everyone? Yeah, same thing that what they have done over here. Great. Now, let's come back to section 4.2.3. See, Oersted said that moving charges produces magnetic field. Right at the beginning only, we have discussed this. Oersted said that moving charges or currents produce magnetic field. And then we said that, okay, listen, we have to find how this field affects moving charges or currents. This part we just did, which is the Lorentz force. This part is what we are going to see now. We just did how magnetic field affects motional charges. Now we have to see how magnetic field affects current carrying wires. So let's come to that particular point. Right over here only. They have mentioned all these things and they have done some small derivation over here, and then they finally come up with some answer or solution. So what exactly have they done? Let me tell you that. See, simply put, if you have a current carrying wire, and let's assume that the direction of the current to be like this. I know negative charges go like this, opposite to the current, but isn't it the same as saying an equal amount of positivity, an equal amount of positive charge goes like this, So these positive charges are traveling with a drift velocity. I hope you remember drift velocity, which you have done in current electricity, and each charge being plus E like this. So they are moving with basically the drift velocity. I hope this is absolutely clear. So if moving charges can experience force, a current carrying wire is also moving charges, so that will also experience force. So I can say that the force on the charge carriers, will be nothing but the charge, in this case, is nothing but E into velocity of them, which is nothing but the drift velocity, and then it will be crossed with nothing but our magnetic field. That will basically give me the force on any of the charge carriers. But there will be many such charge carriers. In even a unit volume, there will be so many such charge carriers. I hope you understand that. So if you add all these forces, on all the charge carriers for that wire, so the force on the current carrying wire is the sum of all the forces on all the charges, and that force on that particular wire which carries current is given by I, okay, I, and then you have basically the length of the wire, and then you cross product it with the magnetic field. That's it. That is the final answer. So the force on a wire carrying current is given by I L cross B. This is the force on a current carrying wire, which is the sum of all the forces on the moving charges. This is exactly what they have given. Now usually what happens, our wire may not be straight, it might be basically bent. So what happens is, usually you do not end up blocking this. Rather, you say that, listen, my wire might be big like this, it is carrying some current I. You take a small part of that wire, which has a length of dl, and it is carrying that same current I, and maybe magnetic field is going like this over there. So it will experience some force in the direction of L cross B. Length is here, magnetic field is here. If you do the cross product, it will come towards you. So there will be a small force like this. It will be dF. So the force on the element of that particular wire is dF, and this dF technically is current into that small element which is dl, and you cross product it with the magnetic field. But when you want to find the net force on the wire, on that particular wire, that force on the wire will be the sum of all these forces, which means integration. Integration is summation. So therefore, you will see it will be always the net force on that particular wire will be integration of that current into dl cross the magnetic field. This is the main answer. This is your small answer. This is force on a small part. If you want to find the net force, you will have to sum up, add up, integrate all the small chintu-mintu forces to find the net force. That is what it means. I hope this is clear. This is the main statement, and this is exactly what they have mentioned. This summation can be converted into integral for most cases. So this is the net force, which is I integration cross of length cross B. So they have written it in weird forms over here, but we have made it look very straightforward and simple. Okay, till this point clear? This formula, use it only for a straight wire. This formula, preferably use it for a straight wire, because then when you have a curved wire, what is the length, right? So it will not be the length in a curved manner. So use it for a straight wire. If the wire is bent, then you have to basically, use this integration. Okay, let's see a simple example right over here. There is a wire whose mass is 200 grams, not much. Length is 1.5 meters, it carries 2 amperes current, and it is suspended. Imagine a wire floating in air. Isn't it crazy? And why is it floating? Because of the magnetic field which is traveling inside that plane of that board. What is the magnitude of the field? Okay, so there is a magnetic field which is going, there is current which is going, and the weight is being balanced. So this problem has to be solved by drawing or showing all the forces. Obviously, the weight will act down. There must be an equal and opposite force so that it stays in equilibrium. How do I know it's in equilibrium? It's clearly mentioned, it is suspended in mid-air. Means it is balanced. Who will balance it? IL cross B force. I length cross B force. See, the length of the wire is here, magnetic field is inside. So can you tell me what is the angle between the length and the magnetic field which is inside? The length and the magnetic field which is inside. Clearly it is 90 degree. Clearly it is 90 degree. So my dear students, this magnitude will be ILB sine 90 being 1, it will just be ILB. So clearly ILB is equal to mg, rather B is mg divided by IL. Mass 0.2 kg, G is 10. Current how much? 2 amperes. Length is nothing but 1.5 meters. Point goes off with the 10, 2 cancels, 1.5 is nothing but 3 by 2. So it will be basically 2 by 3 Tesla. So magnetic field is basically 2 by 3 Tesla or 0.66 Tesla. Yep. I hope this is absolutely clear. Everyone? Yep. Correct, Madhumati? Yes, Atluru? Awesome. Now in the actual question, what they have done is they have taken the G value as 9.8. So they have got slightly less value. But we have taken the value of G as 10. So we have got slightly higher value, which is 0.66. So that's okay in the NEET exam or in the board. So you have to assume something. Either it will be given or generally you take G as 9.8. Unless the options are not matching, then you go to G is equal to 10. Yep. In NEET exam, all those things don't happen. Cool? Okay. So this is what we had done. Now there is one interesting thing I'll tell you about wire carrying current, especially if the wire is curved. A lot of people, will suffer if they do not know this trick. Imagine this is a curved wire and this curved wire is placed maybe in some magnetic field, maybe it is going inside, and let's say it is uniform, for example. This is uniform magnetic field. If I want to find the force on this particular curved wire, you know what you can do? You can just find out by taking a straight line carrying that same current, a wire replacing that curved wire with a straight wire. This is like distance, this is like displacement. You just find the force on the straight wire. On the straight wire. Your job is done, which will then be basically current into that effective length cross producted with that magnetic field. That's it. This makes the job very, very easy. So this is a very, very important simplification which you should know. There is another direct application of this. Imagine you have a loop carrying current. What is this? This is a loop of basically current, and maybe there is magnetic field which is probably headed like this, maybe. Who knows? This is again your uniform magnetic field. For such a loop, instead of a curve, the final point is the initial point. That means what should be the effective length? What should be the effective length? It will be the 0, because the start is the end. The end is the start is the end. So the effective length is 0. So if you had to replace the loop, you will replace it with nothing, because there is no start or end, it is just 0. So hence the force acting on any such loop in a uniform magnetic field is 0. Again, a very, very important statement. This is a result of this then. Isn't it amazing? A uniform magnetic field will never apply a force on a current carrying loop, but it will apply a force on a curved wire. There are many such examples which are based out of it. Say, you have a semicircular wire. You have a semicircular wire carrying current, let's say like this. You have to find the force acting on this particular semicircular wire. So what you do is basically forget it is a semicircular wire, replace it with a straight wire carrying that same current, which means when you replace it with this, in that same magnetic field, of course, in that same magnetic field, the length which is there effectively now from here to here is the diameter, which is basically 2 times the radius. So therefore, that force will be, current is there, length is basically 2r, magnetic field is inside, the angle between the length and the magnetic field is inside, length is here, is 90. So it will be basically sine of 90 degree. Hence the force will be 2IRB. Hence the force will be 2IRB. Got it, everyone? Cool. How easy it is to solve the problem by using this simple property. Not just that, there were very tricky questions also which I have seen in NEET or probably even in CBSE they can ask you. Say there is a wire which comes in like this. Okay, we'll do one thing. The current comes in from here and the current goes out from here, and the magnetic field, of course, is like this, and it is uniformly present everywhere. Magnetic field is present everywhere. This is a square. So you have to find the force on the square of side length A. That is the question. Force on the square only. Don't calculate the force on the outer elements, okay, whose side length is A. Now you will be like, sir, it is a loop, sir. And you just told me whenever it is a loop, the net force acting on it is 0. Sir, so the answer should be 0. Right? That is what one would normally guess. But be little careful. Be little careful. In a loop, the current starts and comes back to the same point. This is not a loop. Please understand. Even though it looks like a loop, it is not a loop, because actually speaking, the currents are not traveling like this and coming back. Rather, the current over here is getting distributed like this and like this. I by 2 and I by 2. Half here and half here. Is that so, everyone? So be very careful. So now you find the force on any one segment, you can say that the same force acts on the other part. So if you multiply by 2, you will get the net force. So say, for example, you just find the force on the upper element, which has the current of I by 2, side length is A and side length is A. This diagram is a bent wire, is a curved wire. You can replace it with a straight wire. You can replace it with the same wire carrying current I by 2. How much will the length be? Well, if you think carefully using Pythagoras theorem, if this is A, this will be nothing but A root 2. A square plus A square is 2A square, so it will be A root 2. Got it? So this is a common mistake, otherwise you would get the answer as 0. So now think as if this is placed in that magnetic field. How much will be the force on this part? The force on this particular part will be I, which is I by 2, length, which is A root 2, into B, into basically sine 90. Sine 90 because angle is 90 degree. So it will be root 2 IAB divided by 2. That is the force on this particular part. But let's not forget that there were two parts. One part was also here. So there was a part here and there was a part here. So both these parts will experience the same force, I L cross B. So one force here and this will also experience the force. They will not cancel out each other. Currents are in the same direction. So therefore, the net force will be 2 times this force on any one part. So it will be 2 times of root 2 IAB by 2. 2 cancels. It will become root 2 IAB. That is the final answer on that square loop. Is that clear? Answer is definitely not a 0. Got it? Did you love this question? Was it an interesting question? Okay, so this is how you find the force on current carrying wires. Force on current carrying wires and loops using this particular formula. Great. Now, let's come back to the force on moving charges, which we just studied some time back right over here. This one, the Lorentz force. And there are some special cases on this. There are some special cases which you need to know, and you will see it regularly being asked in many examinations. So let's come back to that. That is what the next section is all about. So they talk about motion of a charge in magnetic field and the different cases, and then there are problems on it. Let's start one by one. Here they talk about, okay, we consider in great detail the motion of charge in a magnetic field. We have learned the mechanics, blah, blah, blah. Charge particle in a circular motion. So work done is not changing the magnitude of the velocity produced. So by the way, this part I have already done in the starting of the lecture. Okay. Motion of a charged particle in magnetic field, the magnetic force is perpendicular to the velocity of the particle. So no work is done and no change in the magnitude of the velocity is produced, though the direction can be changed. Notice this is unlike the force due to electric field. Notice unlike electric field, which can change, which can transfer energy in addition to the momentum. So we shall consider a charged particle's motion in the field. First, let's consider the perpendicular case, and then we will take the other thing. Okay. Now, you might ask, sir, where did we do this? This particular part. Let me go back and show it to you where we have done. Right at the beginning. Shreyas Sir knew it will come. So Shreyas Sir did it. Force is perpendicular, work done by it is 0, no change in the kinetic energy. So speed, that means magnitude can't change, but the direction can change. The direction can change. But this is not the case with electric force. Electric force can definitely change the speed. We have seen that. It can also change the direction. So electric force can change speed as well as direction, but magnetic force, can it change the speed? No. Can it change the direction? Yes. So a statement based question can come from NCERT. Statement based questions can come from NCERT like this in your NEET exam also. Electric force can change magnitude and direction. Magnetic force can change magnitude and direction. That statement will be wrong. Magnetic force can change speed but can't change direction. That would be also wrong. Magnetic force can change direction but not speed. That would be correct. Is that clear? Give me a thumbs up, then we'll proceed. Give me a thumbs up, then we'll proceed. That is what is mentioned here. So let's start with the first case then. The first case under our consideration. First, consider the case of V perpendicular to the magnetic field. So the particle will describe a circle to each other. Okay, we'll come to that. Say for example, this is how the magnetic field is. It is inside the plane of the board. It is inside the plane of the board. Imagine there is a charged particle Q like this, and it is given a velocity in this direction. Okay, it is given a velocity in this particular direction. Now what happens is, because the magnetic field is there, velocity is there, so it will experience a force. And which direction will it experience the force? Think about it. The force will be V cross B. It will be in this direction. V cross B. The thumb comes out here. So the force will be here. But this can't change the speed. It can only change the direction. Okay. So the particle will basically continue to go maybe like this. It will continue to go like this. Direction is changed, but magnitude is not changed. And this will always happen that velocity and force will be perpendicular, only direction will change, which means this should end up doing circular motion. There is no other option only for it. There is no other option for it. It will end up going in a circular path, and only in a uniform circular motion will you see, no matter where you go, no matter where you go, the force will be perpendicular to the velocity. The force will be perpendicular to the velocity. So this has to be a uniform circular motion, and this uniform circular motion is in a transverse field, transverse magnetic field. I've seen such questions on statement based in some competitive exams. A charged particle in a transverse, meaning perpendicular, meaning normal. You can see velocity is perpendicular, velocity is here, magnetic field is inside, is perpendicular to the magnetic field, then it performs a uniform circular motion. So options were parabolic motion, straight line motion, elliptical motion, circular motion. See, if it was planets, Kepler's laws, then it will go to elliptical motion. If it was maybe a ball dropped, it will be a straight line motion. If it was a ball thrown at an angle under gravity, it will be a parabolic motion. But this is a charged particle thrown in magnetic field, perpendicular to it, it will go in a circular manner, in fact uniform circular motion. Correct. So a uniform circular motion has some parameters which you should definitely know and find out. The first one being the radius and the second being the time period of the motion. So if you want to find the radius, start off with this. The magnetic force provides, because it's a circular motion, you need centripetal acceleration. So it provides centripetal acceleration. So the centripetal acceleration, of course, is towards the center. That's why it is called centripetal acceleration. So the magnetic force is mass into AC. This is your second Newton's laws of motion. So that force will be the charge into the velocity, into the magnetic field, into sine 90. Why? Transverse, clearly mentioned, means 90. Acceleration, we have seen this in circular motion, is V square divided by R. Sine 90 is 1, VV cancels. So it will just become QB is equal to MV divided by R. Therefore, you will see R is nothing but mass into velocity divided by QB. Very important formula which again you are supposed to remember. You can play around with this formula a little bit and write it in slightly different forms, like how mass into velocity is momentum, so momentum divided by charge into magnetic field. Also, momentum is a root of 2 times mass times kinetic energy, so again divided by QB. So if momentum is given, use this. If kinetic energy is given, use this. If speed is given, use this formula. Accordingly, you can use any of them. But if you remember this, it is better because you can get this or this very easily, because those are dependent formulas. You can't sit and remember everything, just remember one thing. That's more than enough. Correct. Right? Now that was the radius, of course. We can also find what is the time period of revolution. We can also find the time period of revolution. So the time period of revolution is given by T is equal to circumference, the circumference of that circle, time is distance by speed, upon that speed. Circumference is 2 pi r, speed is v, but wait a minute, your r is nothing but mv divided by qb. How? I just got it now over here, mv by qb. vv cancels, so I'm just left with 2 pi m divided by qb. That's your time period of revolution. Best part, it is independent of speed. It's independent of the speed. Can be useful in some questions. They might give you a particle is thrown with 100 meters per second. Another similar identical particle is thrown with 500 meters per second. Which one will take more time to complete a circle? The answer will be both will take the same time. Yes, the radius will be different. The one which is thrown with less speed will go in a smaller circle. The one which is thrown in larger speed will go in a big circle. But both of them will come back in the same time. That's very, very important. Okay, this is very, very important. So lower speed versus higher speed, the only difference is the circle's radius. This will go in a smaller circle. This will go in a larger circle, but it will take the same time. Is that clear, everyone? Yep. Awesomeness. Great. So these two components, these two formulas you must remember, guys, for solving problems. Now, I think there is a question on that. Before that, going to the next topic, first I think we'll do this. Yep, this is a very interesting question. What is the radius of a path of an electron and charge moving at this speed in a field perpendicular to it? What is the frequency? Calculate the energy and blah blah blah. This is the question. Let's try to solve this. First part, radius of a path of an electron which is moving in a magnetic field which is perpendicular. I can see the word perpendicular. I immediately know it will be uniform circular motion. Uniform circular motion in a perpendicular magnetic field, exactly like this. Okay. So quickly I jump to the formulas which I already have by hearted. mv divided by qb. Mass is the mass given. Yes. 9 into 10 to the power minus 31. Is the speed given? Yes. 3 into 10 to the power 7. Is the charge given? Yes, it's an electron, so it will be nothing but 1.6 into 10 to the power minus 19. Is the magnetic field given? Yes, 6 into 10 to the power minus 4. All these values, solve this, guys, and see what is the radius that you get. They have, I think, got the radius as 28 centimeters, or basically 28 into 10 to the power minus 2 meters. Basically, you get the radius as just 28 centimeters. So this electron will go in a circle of about this size, 28 centimeters. So it will keep going round and round about this size. That's how you do it. Same way, we can go to the second part. What is the frequency? Frequency is 1 by time period, and time period is 2 pi mass divided by qb. So therefore, frequency will be charge. Where is the charge? Where is the charge? 1.6. 10 to the power minus 19. Magnetic field. How much is it? 6. 10 to the power minus 4 Tesla. 2 into 3.14 into the mass, which is 9 into 10 to the power minus 31. So that frequency, after solving this, you are getting it as 17 megahertz. 17 into 10 to the power 6 hertz. Frequency's unit is hertz. 10 to the power 6 is mega. So megahertz. So just imagine how many times it is going. Not 5-6 times or 17 times. It's 17 mega. So it is 17 million times in 1 second. In 1 second, so quickly, it is going so fast. It's crazy to even think about it. Lastly, they have asked about the energy. Lastly, they have asked about the energy of it. What is the energy? Now, how do you find the energy? Well, there are many ways to do that. See, if you go back to our original formula, you can use this from the radius to find out the energy. Okay, or forget that, you can just say it is nothing but half mv square, because speed was already given, so don't have to break your head so much. It will just be half mv square. So therefore kinetic energy will be half into mass 9 into 10 to the power minus 31, speed 3 into 10 to the power 7 square. But this answer, mind it, it will be in joules. It will be in joules. Yes. So whatever you get, it will be in joules. 9 into 9, that's basically 81 divided by 2. 7 into 2, 14. Correct? And you have 31 with a negative power. So 31 minus basically 14 will be minus 17, 10 to the power minus 17. This will be in joules, but I don't want the answer in joules. I think it is in electron volt. So 81 into 10 to the power minus 17 by 2 divided by 1.6 10 to the power minus 19. The answer will be in electron volt. Finally, you solve the question and you get the answer as 2.5 kilo electron volt. 2.5 kilo electron volt. 2.5 kilo electron volt. That is the answer that you get. Understood how to solve these questions, guys? Everyone with me? Okay. And if you have joined the channel very late, please subscribe. And if you have joined the lecture also late, first of all, after subscribing and probably, you might have missed joining the Telegram group or turning on the notifications, turn it on. And if you are watching it recorded, but watching it sincerely, still kudos to all of you. Very good. Keep it up. It shows your commitment that even if you can't attend the lecture live, for some reason, you're watching it in the recorded manner. Keep it up, guys. All right. Thank you so much. Great. Thank you for liking. In case you have not yet liked the video, please like it. All right. So this was one peculiar case. Now there is another case which we need to see after this, and that is this particular case of, at an angle. So we'll come to that. So imagine there is this charge again, but this time it is thrown with this velocity at an angle to the magnetic field. At an angle to the magnetic field. This is the second scenario. When this happens, what I'm going to do, I'm going to split this velocity into two components. One component of the velocity is here. If this is theta, this would be v cos theta. The other component will be here, which is v sin theta. Now tell me one thing, when magnetic field and velocity are parallel, how much force does it apply? When velocity and magnetic field are parallel, what will happen to v cross b? Cross product will be 0, parallel vectors, sine 0 is 0. So that means what should happen? Won't this component v cos theta be unaffected by the field? Do you get it? V cos theta is basically, this particular v cos theta is nothing but parallel to the magnetic field. So therefore, v cos theta should be constant. Should be constant, since there will be no force only on it. No force on it. V cross b will be 0. Very nice. Okay. But what about v sin theta? Oh, that will experience a force, guys. That will definitely experience a force. Magnetic field is right, velocity is up, so v cross b will be towards you. V cross b will be definitely towards you. So the force will be like this. And this force will be Q v sin theta into b. Q v sin theta into b. Oh, sorry, v cross b was inside, my bad. I did b cross v. So sorry, guys. It will be inside, my bad. Yeah, that force will be inside on this v sin theta. So can I say v sin theta, but v sin theta will change the direction, due to magnetic force without changing the speed, without changing its magnitude, without changing its magnitude. Okay, so how will it look like, you might wonder? How will it look like? Let me show that to you. It's a very, very interesting thing. Just imagine this is your vertical axis. This is the axis which is coming out of the plane of the board. I'm trying to show it in 3D. The force is inwards. That means on that charge, the force is like this. I'm trying to show a 3D view of this. The V sine theta component is over here. The magnetic field is over here. So because of that force, what will happen? This velocity which is there will go like this, and the force will always be perpendicular to it. So it will go in a circular path in a weird direction. Let me show that to you. Try to visualize this. This is in the YZ plane. Are you able to visualize this, guys? It's basically in the YZ plane, my dear students. See if you are able to think about this. It's in the YZ plane. Are you able to visualize that? Think carefully. It's in the YZ plane. Yep. This V sine theta, this particular V sine theta, right? It goes like this, then it goes like this, then it comes like this, it comes like this, goes like this. So it is always V sine theta which is going round and round and round like this. I hope you are able to visualize. But at the same time, the V cos theta is trying to push it in this direction. V cos theta is trying to push it in this particular direction. So because of both of these two things happening simultaneously, what will end up happening is this. It wants to come back to the same point, but it won't. Rather, it will go like this, and it will come back slightly in front of it, and then it will go like this, and then it will come in front of it, and then it will go like this, and again it will come in front of it like this. This motion, where the circular motion is slowly shifting ahead in its axial direction. This is the axis, the x-axis is the axis of the circular motion. It's slowly going ahead. So this is basically called as a helical motion. So when velocity is not perpendicular but at an angle, both these components play a role. The V sine theta is responsible for circular motion. The V cos theta is responsible for the motion along the axis. So both of them combined, it does a helical motion. That diagram is beautifully drawn by me also and by NCERT also. See this, how it is going in a helical motion. I hope you can visualize this. I hope you are able to visualize this. So this particular helix which I have drawn, that helix has many parameters. First is, obviously we can talk about the radius of the helix. We can talk about the radius of that helix. So maybe this would be the radius. there would be radius, then it will have a time period. So radius will be, instead of mv, it will be mv sine theta, because just think about it, this is the radius. Okay, so radius will be mv sine theta divided by qb. Time period still the same, no effect, it won't get affected by speed, so 2 pi m by qb. There is one more parameter, which is the distance from this point to this point, or from this point to this point, or from this point to this point. Basically, after one rotation, how much does it go ahead? That is called as the pitch. What is the meaning of a pitch? After one rotation, how much did I move ahead? Just imagine, I take my hand like this, I am moving it like this. I am not moving, I am just moving my hand. So after one rotation, my hand comes exactly at the same point. But just imagine, I move forward. So after some time, my hand comes here instead of here. So it has moved ahead exactly after one rotation. So from this point to this point, that distance is called as a pitch. So what do you think will this pitch depend on? Obviously my speed. If I move fast, I will have a more pitch. If I move slowly, then I will have less pitch. I will move less. So this particular pitch depends on the axial speed multiplied by how much time I take to complete a revolution. Distance is speed into time. That speed horizontally is v cos theta. So just put v cos theta over here, and the time is exactly this time. So 2 pi m divided by qb. So mainly, don't remember this, just remember this. This is enough. Radius and time period are still the same. Only speed will be v sine theta. Is it clear, everyone? What is the meaning of the pitch? Time period is the same as circular motion, and radius is as it is. Oh, thank you, Madhumati. Thank you, Atluru. Thank you, everyone. Let me hydrate quickly. Thank you guys. What would I do without you? I'll forget even drinking water. है ना? So that's how you should be involved in your studies. That's how you should be involved in your learning. And that's how a teacher should be involved in his teaching. That you forget about all the luxuries in life, or even the necessities in life. Drinking water is not even a luxury, isn't it? So thank you guys. I mean, only because of you, I keep involved. I keep myself, occupied, and I feel myself as lost in teaching, or probably involved in this, platform, or just physics. It's pure satisfaction, isn't it? And I want you to do the same thing years down the line when you guys become a doctor. You should be so involved in your medical research, in treating patients, or whatever work you are doing, that you should probably forget, and probably the patient only should remind you, doctor, did you eat food? Doctor, did you eat your lunch? Doctor, did you sleep? Doctor, did you have water? Isn't it? That would be amazing. Right. So this is that. Moving ahead. That is what is mentioned right over here. Cool. This is fine. Okay. Now we are going to the next part slowly. Here we are talking about the magnetic field due to a current carrying element. So till now, whatever we did, let me show you right over here. How magnetic field affected charges or currents. Now we are coming back to the original part, how a current produces this magnetic field in the first place. So we did this and this. Now we are slowly coming to current producing magnetic field, which was actually given by Oersted long time back. How does this current produce magnetic field? Now we know that a current around it produces magnetic field in circular loops, and magnetic fields are always loops. They never basically end at any point. They are always in the form of closed loops. How much is the magnitude can be found by a law called as Biot-Savart's law. Biot-Savart's law is a law like your Coulomb's law, which tells you what's the field at any point. Newton's law of gravitation also tells me gravitational field and force at any point. Coulomb's law gives me the field or force at any point. So Biot-Savart's law gives me what is the field due to the current carrying wire. What is this particular field at this point due to this current carrying wire, okay, around it. That is what it is. So it is the source of magnetic field. So going ahead, wow, so much done already. Where are we? Here. Yeah. Magnetic field due to a current element given by Biot-Savart's. All the magnetic fields that we know are due to intrinsic moments. Here we shall study the relation between the current and the magnetic field it produces. So basically this particular law, it shows us the relation between the current and the magnetic field that it produces. So there is a conductor, etc. They have described this, and then finally they have given a beautiful formula right over here. So I'm blocking it, where mu naught by 4 pi is the constant of proportionality, and it is dependent on the medium. Okay, fine. So the magnitude of this is given by this formula. This is the more important formula, and the constant value is also given. Mu naught is called as the permeability of free space. The differences are some. Okay, electrostatic. Okay, this is given, and then they start describing different things. All right, let's start one by one. Imagine there is a wire. This is a wire carrying current. Obviously, it will produce magnetic fields around it, and I am interested in finding the magnetic field at any location. So let's say that location happens to be somewhere over here, and every part of the wire is at different distance at different angles. So they might produce magnetic fields also in different angles and different directions. I will first start by finding the magnetic field due to any one such small part of the wire. So if you take a small part of that wire, maybe here, the current is going like this, so that element will also be treated like a vector quantity. That element is dl. So dl element in the direction of the current. dl is a small element in the direction of the current. I want to find the magnetic field here, so I will just draw a line like this, and I will say that, listen, this is the position vector. This is nothing but the position vector of the point where you want to find the magnetic field. Next step, just do the cross product of dl with r. dl with r, you will see the thumb going here. That is exactly the direction of the magnetic field. So the magnetic field at this point is coming towards me, but since it's being produced by a small element, the field will also be very small. Later on, I will see that the total magnetic field produced by the entire wire will be, you take all such elements, you take one element here, you take one element here, you take one element here, you take all the elements of that wire, and each of these elements will be at different distances. Each of these elements will be at different distances, different angles. So you add all those magnetic field due to all those elements. That's it. So it will be nothing but equal to integral of dB. That's it. So the magnetic field as a total will be integral of dB. As simple as that. Is this point clear? You find the magnetic field due to each part, you add them up, you will get the net magnetic field at that given point. How much is that dB? That is given by as follows. This dB is, there is a constant, that constant I will call it as mu naught by 4 pi. Just like you had permittivity, here you have permeability. I'll come to it in a bit. Then you have the term IDL, and then you cross product it with R vector, that is the position vector, and divide it with R cube. This is the vector form, but if you write it in magnitude form, then what will happen is, this will be some constant mu naught by 4 pi. Here you will have IDL R into sine theta. Look at this, the angle between them, if it is theta, then here you will have sine theta. R and R cube will cancel and I'll be left with R square. What happened to that R? It cancelled with this R. I'm just left with R square. So this becomes the magnitude part of it. So this is the formula for the small field due to a small element. What is this mu naught called? Permeability. Permeability of vacuum. And this value is 4 pi 10 to the power minus 7 SI units. Very, very important. This value of mu naught is 4 pi 10 to the power minus 7 SI units. Just like you had permittivity, you have permeability. Remember how the electric field formula looked like? Electric field formula looked like in electrostatics. Try to recollect. You had 1 by 4 pi epsilon naught, and then you had the charge on the top, and then you had distance square. Do you remember this? This was the formula for electric field due to a charge. Very similar looking formula. Instead of epsilon, you have mu. Instead of that constant being down, you have it upstairs. That's the major difference. In fact, throughout magnetism, you will see the formulas are same but different. The same part is this. The different part is, wherever you see epsilon below, mu will be on the top. Wherever you see epsilon on the top, you will see mu below. Wherever you see charge, you will see current into something or the current length combination, ideal. You can see R square here, you can see R square here also. Do you see? Same but different. I'm just comparing it. This is just for comparison. Okay, very important again. This is just for comparison. I'm just blocking it. So permittivity replaced by permeability, distance square inversely proportional, correct. Instead of charge you have ideal. Also notice one thing, charge was a scalar. What is ideal? Ideal is not a scalar, it is a vector quantity. So here charge was scalar, here it is a vector quantity, correct. So these are some minute small differences and similarities that you can see over here. Okay, so that's exactly what they have done by writing over here. Let's have a look. There are some differences, there are some similarities. So if you thought that the reels and the memes that you see, is not read by NCERT people, but I think they were aware of it even in their 90s and maybe even 2000s, because this NCERT dude has written down same but different. So NCERT dude wrote same different, much before GTA 6 and much before the Gen Z. So they are really cool, guys. They are really cool. They were the original memers, isn't it? Okay, so both are long range, both of them depend inversely. Yep, perfect. Both of them depend inversely on the square of the distance from the source. This is definitely true. Electrostatic force is produced by scalar charge, whereas magnetic field is produced by a vector source ideal. This is something which I just told you over here. Field produced by scalar, magnetic field produced by a vector, which is ideal. Perfect. That is what they have told right over here. That part done. Next important thing, electric field is along the displacement vector joining the source, whereas magnetic field is perpendicular to it. So electrostatic field is along the displacement vector, whereas the magnetic field is perpendicular to the plane containing the vector, and that's blah blah blah. What does this mean? Going back over here, do you remember electric field is in the direction of that position vector? If this was R, wherever the position is, in the same direction the field also is there. But magnetic field is not like that. If you are here, it is perpendicular. If you are here, it is perpendicular. So that is what they are basically telling you at this point. Yes. So if you are here, the magnetic field is not in the same direction. Rather, it is in some perpendicular direction only to this particular plane. Whereas electric field is in the same direction of where you are. That is what this particular point says. There is an angle dependence which is not there in electrostatic field. Yes, angle dependence in the Biot-Savart law which is present, which is not there in electrostatic case. That is also seen. Look at this, sine theta is there here, there is no sine theta here. So angle dependence is there between the position and that element. That is not there. Cool. Same but different. Also they tell you that there is a relation between this and this, which is given by this particular formula. So let me just block it. Actually, you don't have to remember this now because they have clearly mentioned we will discuss this in chapter 8, in the chapter 8 of electromagnetic waves. So what is it that they are telling me over here? What is it that they are telling me over here? They are telling me, if you know permittivity, I can find out permeability. If you know permeability, you can find permittivity. The formula goes like this. Speed of light square is 1 by epsilon naught into permeability. So if I know this, I can find this. If I know this, I can find this. That's all that they are telling. So this is nothing but your speed of light. Speed of light, which is 3 into 10 to the power 8 meters per second. That's exactly what they are telling. Okay. C square in 1 by epsilon naught mu naught, or epsilon naught mu naught is 1 by c square. Okay. Thank you Madhumati, thank you Krishna, thank you Atluru Warrior Pandus. Great. Okay, let's see a question based on Biot-Savart's law. A very nice question coming up on your screen. There is a current which is placed element at the origin, carries 10 amperes. What is the magnetic field on the y-axis at 0.5 meters? Delta x is 1 centimeter. Let's visualize this, guys. So maybe it's a long wire. I'm just taking a small part of it and the current is going in this direction. If you talk about this, this is IDL and this IDL is same as I delta x. This current is 10 amperes. Delta x is 1 centimeter, meaning 10 to the power minus 2. So technically it is 0.1. Technically it is 0.1. I want to find the magnetic field here. That means this is my position vector. This is my position vector, which is 0.5 meter. Next thing, the angle between this and this is 90 degree. So theta is 90 degree. If you do dl cross r, the thumb comes outwards. So hence the magnetic field at this point is towards you. So if you ask me what is the magnitude of this, well, we have already seen the formula. It was mu naught by 4 pi. Then you had what do you say, I and dl over here, and then you have sine theta over here, and then r square over here, correct? This was the formula which we have seen. So start substituting values. This is 10 to the power minus 7. This is nothing but 10 to the power minus 7. Current into dl is nothing but 0.1. Then sine of 90 degree, sine of 90 degree, whole thing divided by this distance, which is nothing but 0.5 and square. That's it. That will give me the small amount of magnetic field. This is 0.1, this is 0.5. 0.5 is basically half. Half square is 1/4. 4 will go on the top. So I'm left with 10 to the power minus 7, 10 to the power minus 1, sine 90 is 1. So 4 goes on the top. So this will be 4 into 10 to the power minus 8 Tesla. That's what the formula value is. 4 into 10 to the power minus 8 Tesla. Okay. Yeah, it is extremely small due to this small part of the wire. So this is how you can use Biot-Savart's law for finding magnetic field. Very straightforward. Okay, I hope you learned the application. And my dear warriors, my dear Pandus, we are doing all the in-text questions in these NCERT series. That's very important, and you might be wondering why. This is of very high significance. You will see in many of these competitive exams, they directly end up picking questions from here, and many students skip this thinking this is solved examples. Yes, they are solved, but not by you. They are solved by the textbook makers. So you too have to solve it. So it's for you. And they directly pick up questions by changing the values. Great. Now there is a very nice, interesting application of this Biot-Savart's law, okay, which we have studied over here, for finding the field due to different geometries. And they try to find the field due to a circular loop on its axis, and then they show the field diagrams, and they also find the field at the center of it. Let's try and understand it. So let's say we have a loop like this, and let's say the current goes like that, comes like this. You will see that okay, if this is a loop carrying current, this is also called as the axis of the loop. Axis of the loop. This is a current carrying loop. The magnetic field due to such a loop looks somewhat like this. Observe it very carefully. It comes like this, goes over here, goes like this, goes over here. This is how the magnetic field lines look like. This is how the magnetic field lines look like. As you can see, if you are close to the center over here, it's very, very strong. This is the center where it is basically strong because the field lines are very close enough to each other. Very far away from the axis, it starts becoming slightly weaker as they are diverging in nature. And because the magnetic field lines are coming over here, this is often on the right hand side, on this side, because of the direction. This is the north pole of that electromagnet, and because it is coming in from here, this is the south pole. So basically the behavior is just like a bar magnet, where this is the south pole, this is the north pole. So that's why this current loop is also called as an electromagnet. This is your permanent magnet. This is your permanent magnet because it shows those properties forever. It shows those properties forever. North pole, south pole are there. This is electromagnet because only when you supply electricity, these poles are developed. If there is no electricity, these polarities go away. So you can turn on the magnetic properties on and off by turning on or off the current. Here you can't do that. It's a permanently made magnet. Is that absolutely clear? I hope you loved this diagram. Yes, thank you, Krishna. Hi, Gulshana. Welcome to the Vedantu NEET English channel. Yep. Now, how much is this field is what we are interested in. How much is this magnetic field is what we are interested in. So this is a current carrying loop. Okay. This is the axis, and let's say I am here. Oops. I am here somewhere on the axis. This distance is basically x. This distance is basically x. At this particular point, this radius, this is your radius, and at this particular point I want to find what is the magnetic field. Okay, I want to find what is the magnetic field. So here is what I will do. First of all, I will take any element of the current. Let's say on the top, this is my small current element, which is IDL. Okay, a small current element. If you visualize this in 3 dimension, you will realize actually IDL is along the Z axis. Try to think about it little carefully. You will see why it is along the Z axis, because it will be like this. This particular axis. This is your Z axis, this was your Y axis. Are you able to visualize this? So imagine IDL is actually on the top, but it is coming towards you. You want to find, due to that element, at that point over there. From here you are looking here. From there you are looking here. What is the magnetic field there? So how will my position vector look like? My position vector will look like this. This is basically your R. This is basically your R. Now just do IDL cross R. Current DL is there. Position vector is there. IDL cross product with R. I think it will come like this. The thumb is going at an angle. Just try it out wherever you are sitting. Just imagine current DL is going here. The position vector is going there. It's not horizontal. It's downwards. So when you rotate your fingers, not horizontally, but slightly bend your hand and then rotate it, the thumb will go at an angle. See if you are able to do this. See if you are able to do this, then you will notice that this is the vector that we are talking about. So this is a small magnetic field which is generated. This is a small magnetic field which is generated, and this magnetic field, if you ask me the magnitude of it, it will be mu naught by 4 pi. You have IDL as it is, and divided by R square is there over here, and here you have sine theta. But what is the angle between these two? IDL is towards you, R vector is down. So if you think about it, it's actually 90 degree. It's actually like this. It's in a inclined plane. One is here, another vector is here. So it's actually 90 degrees if you think about it. So hence sine 90, or else people take this angle and do some nonsense. No. So this is basically your dB vector. So it is mu naught I dl divided by 4 pi small r square. Now this dB which you are seeing will obviously have two components. This dB which you are seeing will obviously have two components. One component of this is horizontal. The other component of this is here. Imagine you take all such elements. Every time you take an element, this green component is always there in the same direction, but this red component once is here, once is here, here, in all possible directions. If you take the element here, that component is here. If you take the element somewhere else, you will see the component, red component will keep changing the directions, and it will be there everywhere in a circular manner. Just try to visualize this. Just try to visualize this. If you take many such components, what will happen? It will be there like this, probably. Once it will be also there here, it will be there here, it will be also there here, it will be 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 there here. It will be there equally everywhere, but this horizontal component will always be in the same direction. So doesn't it mean that all these red components will end up cancelling out each other? Won't they end up cancelling out each other? Are you able to visualize this, everyone? So they will end up cancelling out each other. So the red ones components cancel, but the green ones do not. So just worry about what is this dBx. Well, if I measure this angle to be theta, this angle is 90 minus theta. This angle is 90 minus theta. This is again theta. This is 90 minus theta. And again, this angle is theta over here. So that is how the geometry works. This is 90. So theta, complementary, theta, complementary, theta. Okay. So dBx is basically dB's cos theta component. But we know that the net field will be integration of only the x components, nothing else. So it will be integration of what is dB? Mu naught I dl whole thing divided by 4 pi r square. What is cos theta technically? Cos theta adjacent by, oh, there is one small mistake. Let me rectify it everywhere. I should use different symbols, capital R and small r, or else it will create a lot of confusion. Radius of that loop versus small r is completely different things. So let's write it only separately. Okay. Cos theta is adjacent, which is basically r, divided by hypotenuse, which is basically small r. Is that right? So this formula will just become r by small r. Now out of all these people, only dl is a variable, current is same, mu naught 4 pi r, everything is a constant. So put all these gentlemen outside. Mu naught I r divided by 4 pi small r cube integration of dl. All of them were constants. So just put it outside. Don't do anything. You might be wondering, sir, smaller, how is it a constant? Always, no matter whether you go like this, like this, like this, like this, all these distances are equal. It's like the surface of a cone. So they will all be equal. Okay. So mu naught I r divided by 4 pi. What is small r? This r, actually, if you see, it is a hypotenuse. So won't it be root of r square plus x square? R square plus x square. This is hypotenuse, if you notice. So just substitute this as your r square plus x square, root of it, that means half. But remember that whole thing is raised to 3. So just put 3 over here. So actually half because of the root, but 3 is also there. What is integration of dl? You add all the lengths, you will get the circumference. So it is nothing but 2 pi r. 2 pi r. 2 pi, 4 pi cancels. So final answer will come out to be mu naught current r square divided by 2. And then I have r square plus x square. That is your net magnetic fields derivation. That is your net magnetic fields derivation. Got it, everyone? So complex derivation, I hope I have made it very simple for you. It looks like you have to integrate some crazy stuff, but actually there was no integration involved much at all. So now coming back to this, the magnetic field, oops, what happened to this? The magnetic field on the axis is given by mu naught. If you notice, mu naught is there, divided by 2. Then you have the current into r square, the whole thing divided by r square plus x square, r square plus that distance from the axis square, the whole thing raised to 3 by 2. The whole thing raised to 3 by 2. Yep, whole thing raised to 3 by 2. This is the formula. Now this is something which you are supposed to memorize. Looks like the electric field on the axis of a ring in electrostatics. Very, very similar. Very, very similar. Now what happens if you are at the center? If you are at the center, when I say I'm at the center, that means over here. At the center, think about it. At the center, what will happen to the x coordinate? The x coordinate will just become 0. So just substitute this as 0. Anything plus 0 is that anything. So this formula at the center, what will it be? Mu naught current r square divided by 2. R square plus 0 is r square, whole thing raised to 3 by 2, which is mu naught current r square divided by 2. 2 cancels, so it will just become r cube. R square cancels, so you will be just left with mu naught I by 2r. So that's the magnetic field at the center, guys. Magnetic field at the center of a coil. Again, a very important thing, this field will be over here. This field will be over here. These two formulas are something which you should remember. Is it absolutely clear till this point? Yep. Okay. Jasmine, we are just coming to the end of the lecture, just few more minutes. Yeah. So before the break, I think you will see the lecture only ending. Now, what happens is, see, if you have a complete loop carrying current, let's say like this, you use your right hand rule, the fingers are curling like this, the thumb is coming towards you. So at the center, the magnetic field will be like this at the center. So the magnetic field at the center will be mu naught I by 2 times of radius, where this is the radius. This is basically your radius. This is the current. But what if I don't have a complete loop? Or what if I have many loops? So you accordingly, just change the problem. Say for example, imagine it's having many turns. It's having n number of turns. If it has n number of turns, what will happen is at the center, the magnetic field will be mu naught I by 2r, mu naught I by 2r, just multiply it with n, the number of turns that it has. It's a coil, that's it. Similarly, if it is not having n turns, rather it's just a, can't do that here, is just an arc. Is just some arc which is carrying some current. It's just some arc of the wire which is carrying some current, and let's say this is how it is. What you will do? This arc will contribute some part of that complete circle. If it is a semicircle, it will contribute half. If it's a quarter circle, it will contribute 1/4. So it depends on what angle is there right over here. So if you try to find the magnetic field again, it will be mu naught current by 2R, but instead of the complete circle's contribution, it's a part of the circle. How much part of the circle is it? Think carefully. It will be basically theta by 2 pi. What is this? This is the fraction of the circle. Fraction of the circle. It makes sense. Example, if it is a semicircle, theta will be pi radians. So what will be theta by 2 pi? It will be pi by 2 pi, which is basically half. Makes sense. It's half of the circle. You can directly multiply it by half. You don't have to remember this formula. If it is 60 degree, what will it be? 1/6 of the circle. 60 is pi by 3. So pi cancels. Pi by 3 into half will be 1/6. That pi has cancelled. So 1/6. So it's 1/6 of the circle. That's it. So it's a fractional part of the circle. That's how you can solve those questions. Got it? Yeah. So these again are very, very important for you to remember. This is for n turns. This is for an arc. That's all. So there are some nice questions on this. Let's have a look over here. There is a wire which carries 12 amperes of current which is bent into a semicircular arc of radius 2 centimeters as shown. Consider the magnetic field of the center of the arc. What is the field due to the straight segment? What is the contribution of B from semicircle differs from that of a circular loop, and in what way does it resemble? Would your answer be different if the wire were bent into a semicircular arc, the same radius but in the opposite way as shown in the other figure? Okay, let's do one by one. Let's do part A first. Let's concentrate on this part. What is the magnetic field due to the straight segment? Now if you see this straight segment, this current and dl are in this direction. I am trying to find the magnetic field at the center. So this is my position vector. Can you tell me what will happen if I do the cross product of I dl multiplied by r? Why am I doing it? You might ask. It's because of Biot-Savart's law, nothing else. Just I'm trying to use Biot-Savart's law. So it has numerator I dl cross r. That's it. So if I apply that, what do you think will happen? What do you think will happen? This answer obviously will be big fat 0 because sine 0 is 0. There is 0 degrees between them. They are parallel to each other. So the straight parts, the straight wire on its line or basically axis has no contribution in the magnetic field. So even this part does not contribute over here. There is no contribution at all. Got it? So if you take any wire carrying current, you will see at this point the magnetic field will be 0 on that particular axis. Is the first part absolutely clear? Then can we go ahead? Yeah, they don't contribute. Perfect. Let's go to the second part now. The second part, B, in what way the contribution is different to the semicircle, different from the circular loop? See, semicircle means the contribution will be exactly half. So for the semicircle, if you take for the complete loop, it will be just into half. So it is mu naught I by 2R into half. this thing we have just seen right over here. If it's an arc, it's a fraction of that circle. That fraction being exactly half. So this number is very important. It is half of the circle. That is the answer for the second question. Now let's come to the third part. Would your answer be different if the wire were bent into a semicircle of same radius in the opposite way as shown? This versus this. Well, here, if you curl your fingers like this of your right hand, curl your finger like this, the thumb goes inside. That means the magnetic field was in the direction of that thumb. So that is how the field will be. Here, if you curl your fingers like this, the thumb comes towards you. That means the magnetic field will be in the exact opposite direction. So the direction has become opposite, but the magnitude obviously will remain the same. So hence that is the answer. That is exactly what they have said. Same direction, opposite direction, same magnitude. Okay, it will be half of this, and this is not going to have any contribution. So these were the three important questions, NCERT exercise 4.5. Let's go to the next question. Consider a coil of so many turns, radius, current. What is the field at the center? The moment I see turns, I remember this theory. If it has many turns, I have to use just this formula because each coil will contribute the same. So that's all. So the formula that I will be using will be mu naught I by 2R just multiplied by n. Mu naught is 4 pi into 10 to the power minus 7 divided by 2 multiplied by the current. Current is 1 ampere. Okay. Radius 10 centimeter, which means 0.1 meter, multiplied by n, that is 100 turns. That's it. So 4 by 2 is 2. So 2 pi. 0.1 is 1 by 10. So it will become 10 to the power minus 7 into 10 into 100. This will become 10 to the power 3. And this is minus 7. So it will become minus 4. So this many Teslas. So 2 pi 10 to the power minus 4 Tesla. Yeah, 2 pi 10 to the power minus 4 Tesla, which is 6.28 10 to the power minus 4 Tesla. Perfect. That is how you do it. Just that this number n has come in play. That's all. Cool. Everybody with me? Awesome, guys. Awesome. Now this part, starting from Ampere's law, we'll be doing it in part 2. There are many things over here. Ampere's law, then the solenoid, then the toroid, force between two parallel currents, torque acting, okay, then circular loop as magnetic dipole, then this thing, your galvanometer functionality, all these things in the second part. So today we have done till here. This will come in part number 2. Okay. So we take, proper time to complete every chapter. Line by line we have gone, paragraph by paragraph, so that you understand everything with even additional examples to make you understand the concepts. You attend these series properly. If you say that you are getting less than 90 or 95 marks, I won't believe it in board exams. And yes, there will be also practice session for your boards as well this year, because a lot of 12th standard students are attending. And if you are a 12th standard student, let me know in the comment section after the video is over, sir, we need help for boards as well. I know there are a lot of dropper students here, but just think, when you were in 12th, had these series been there, and imagine somebody helped you for NCERT, it would be so helpful, and also it would have helped you in that NEET exam then and there itself, and you would have cleared it there. So guys, motivate all your juniors to be a part of this channel, and all the 12th standard kids, I want your comments down there that yes sir, when the board exam comes close by, we need help in the PYQs and some mock papers of physics. Cool. Take care guys. Have a great time. Have a lovely dinner. This was your Captain Shreyas Sir. And yes, do not forget one important thing. Some of you have forgotten that. Yeah, like, subscribe, very good. But one more thing. You have to register for the MVSAT in case you have forgotten. enter your name, class, board, etc. Online, offline, online test in October, offline test in your nearest Vedantu learning centers. 20 centers plus are there in India, and get maximum scholarship up to 100%. Even if you are a part of Vedantu and you have joined the courses recently, you will get that scholarship, guys. And yes, a lot of prizes to be won and lot of goodies just for attending the test. And of course, you are competing with the brightest minds, and you will get a all India level score, report card, and performance, scorecard as well. So do not forget to take the MVSAT. This opportunity does not come again and again. It's just a 1 hour examination. It's not 3 hours, 20 minutes, just 1 hour. Okay, so need that 1 hour of yours, and the syllabus depends on which grade you are in. Take care, guys. Bye bye. Hasta la vista.